Okay, so let's start our next topic then. We're done with binomial expansion, quadratic, circular measure, trigonometry, and coordinate geometry. Now, today we're starting our next topic, which is differentiation. Now, today we are primarily going to understand what differentiation is about. And then from tomorrow, we will be discussing some rules of differentiation and how to use that to solve different kinds of problems. So there's this concept that they have recently added to the syllabus, not very recently, that like 3-4 years back, that they want you to understand where this differentiation process comes from. So some background of differentiation, they also want you to understand that. So that's what we're going to start with today. You will not find many questions on this in the past papers. There's like 2 questions until now in the last 3 years. But it's an important thing because that's part of the syllabus. Very straightforward in terms of the questions that they ask. But this background is going to be helpful to understand the differentiation rules later on as well. So let's start with this. Introduction to differentiation. So first of all, we need to understand what differentiation is all about. Now, we've done coordinate geometry, and that was the last topic that we did. What did we do in coordinate geometry? For instance, if we had to find gradient of a line, how did we used to do that? Let's say if we have a line like this and we have 2 points on the line. If somebody was to ask us what's the gradient of this line, how would we calculate that? You would take 2 points. Let's say this point here is 1 and 4, and we have another point on the line that is maybe here, and this point is -1 and -1. Sorry, -1 and 1. These are 2 points that I have on the line. How do I find gradient of this line? I can say gradient is going to be y2 minus y1 over x2 minus x1. So I can call this x2 y2, for instance, and this x1 y1. Gradient turns out to be y2 minus y1, which is 4 minus 1 over x2 minus x1. That's 1 minus minus 1. That's 1 plus 1. And that gives us 3 over 2, which is 1.5. That's the gradient of this line. It turns out to be 1.5. So if I had to find the gradient of the line, I would just use this formula, y2 minus y1 over x2 minus x1. Okay. Now, instead of that, what if I had a curve like this? What if I had a curve like this? So this is the curve that I've drawn on Desmos. And this curve has this equation. It's y equals x squared. That's the function, y equals x squared. Okay, that's what this graph represents. It's a graph of y equals x squared. It's a quadratic function, U-shaped graph, passes through 0 like this. And it's a curve, okay? Now, we have y-axis here, and we have x-axis here. If I were to ask you, what is the gradient of this curve? What would you say to that? What's the gradient of this curve? Any idea? What's the gradient of this curve? How would you answer that? Can you give me a number for that?
2.
2? Is the gradient of this curve 2?
Yes, sir.
Is the gradient 2 at every single point? Is the gradient 2 here? At this point? Is the gradient 2 here? Is it here? Is it 2 here?
Sir, then it
The
can be any number.
Yeah, so the gradient at every single point on this curve is basically different. So that question in itself does not make a lot of sense because it does not have a single value for gradient. The gradient at every single point on this curve is different. Okay, so how do you then find the gradient at a particular point? So since every point has a different gradient, what we can do here is we can find the gradient at one point at a time. So for instance, if we take this point, or let's take this point here, for instance, Let's say this point has coordinates 1 here, a 1x coordinate here, and one y coordinate. So this point is 1 and 1. If I had to find the gradient at this point, remember what you used to do in O levels for this? How would you find the gradient at this point? You would draw a tangent, right? And graphs of functions topic, you used to draw tangents like this. You would draw a tangent in this direction. And then what you would do would be, you would say, let's take 2 points on this line. Take 1 point here and maybe another point here. Find the gradient of that tangent. And that would be an estimate for the gradient of the curve at this point, right? That's what you used to do. That you would draw a tangent and take 2 points on that tangent. The gradient of the tangent at that point used to give you the gradient of the curve at that point, because that's the definition of a tangent. The direction of tangent is the same as the direction of curve at that point, right? That's what you used to do in O levels. But remember, that was a process that could contain errors, because your tangent would be a human drawing, right? And it could have some human error as well. That's why in the marking scheme, you always had a range of values that was acceptable, because I could be getting a different gradient. So for example, I could be getting a gradient of 1.9 at this point. Somebody else might be getting a gradient of 2.5, because everyone would be drawing a slightly different tangent. So that was a process that included some margin of error, basically. What we want to do is we want to find the exact gradient at this point, exact gradient at this point. How do we do that? We do that using differentiation. Now, how does differentiation work? That's what we want to understand first. Now, differentiation works like this. This process works like this. We think of it in this way. We say, let's call this point something. Let's call this point A. This point has coordinates 1 and 1. Let me write that here. What we want to do is we want to find the gradient of the curve at the point A. And the point A has coordinates 1 and 1. This is what we want to find. Now, let's try to figure out what this gradient value could possibly be. Now, what I'm going to do is I'm going to say, let's take another point on this curve. Let's say that point is here. And this point has an x coordinate of 4. Now, if the x coordinate is 4, what about the y coordinate? The corresponding y coordinate, what would that be? If this is 4, if you put 4 here, the corresponding y coordinate turns out to be 16. Let's call this point something. Let's call this point B, for instance. This point is A. If I were to draw a line from A to B like this and find the gradient of AB, what do you think? Let's actually find this gradient first of all. Let's see what that turns out to be. Y2 minus Y1. So we say that's 16 minus 1 divided by 4 minus 1. What does that give us? 15 over 3, and that's 5.
Sir,
Is that a good estimate? Is that a good estimate for the gradient of the curve at this point A? What do you think about it? Is that a good estimate? Is that a good estimate for the gradient of the curve at point A? Yes, Abdullah, what are you saying?
sir, I was saying that if we draw a line between A and B, wouldn't it be a distance that we will be calculating? How can we calculate gradient?
I'm not sure what that means. A, B is a line. We can find gradients of lines, can't we? We can find anything for this line. We can find midpoint, we can find distance, we can find gradient. We are saying we are finding gradient of AB. Okay, so maybe you're getting confused with the notation. If you have AB written, that means distance, yes, but we're saying gradient of AB. That means gradient of AB,
Okay, sir, got it.
right? Okay. Now, if we find the gradient of AB, if you think about it, is that a good estimate for the gradient of the curve at this point? Well, not quite, because the gradient of the curve, the tangent at this point would be like this, and AB is quite off from that, right? It's not a good estimate. Now, what if I were to take another point instead? Let's call that point C, and I'm taking the x coordinate of C to be 3. What about the corresponding y coordinate? The corresponding y coordinate would be 9. If we put 3 here, the corresponding y coordinate turns out to be 9. What about the gradient of AC? What does that turn out to be? Gradient of AC, if I were to draw a line here from A to C and find the gradient of this line. Let's see what that is. That's 9 minus 1 over 4 minus 1, which turns out to be 4. Is that a good estimate for the gradient of the curve at this point A? It's still not very good because, again, the tangent was like this. The tangent's direction was this. And AC is much steeper than that. It's still not a very good estimate. But is it better than before? Is it better than 5?
Sir,
It's better than before, right? It's better than before. Yes, Abdullah?
sir, isn't AC's gradient 8 over 3?
Sorry, I'm sorry. I wrote that wrong here. It's supposed to be 3 minus 1. So yeah, it's supposed to be 3 minus 1, not 4 minus 1. I wrote 4 there by mistake in the denominator. It was 3 minus 1. So that's 8 over 2 basically. 8 over 2 is 4. Okay. All right. So gradient of AC is 4. Now, is that a good estimate? That's also not a very good estimate. However, it's at least better than before because it's closer to the direction of the tangent. This was the direction of the tangent. AB was far away from that. AC is much closer to that, relatively close to that. So 4 is not a very good estimate still, but it's better than before. Now, using this idea, if we could keep bringing this C closer to A, the estimate of the gradient would keep getting better. So for instance, if I were to take another point here, let's call that point B, and that point B has coordinates 2 and 4, right? X coordinate could be 2. When X coordinate is 2, Y coordinate will be 4. If I were to take this point and find the gradient of the line AB now, that line would look like this. This is the line AB, right? I could find the gradient of this line AB and see what that turns out to be. Gradient of AB, let's see what that is. That will be 4 minus 1 divided by 2 minus 1 now. That's 3 over 1, which turns out to be 3. Again, we can say that this is better than before. It's even better than before. This value is going to be closer to the actual gradient of the curve at this point. And the idea is we keep making this point closer and closer. Let's call this point D instead. I'm sorry, because we've already used B above. Let's call this D. The gradient of AD is even closer to the gradient of the curve at that point. So the idea is if we keep bringing the second point closer and closer to A, the estimate of the gradient is going to keep getting better, right? So if I were to take another point that's even closer, let's call that point E. I can't really show that in the diagram because it will be extremely close, so it's not going to be visible. Let's call this point E. Let's say that was 1.1. What would be the corresponding y coordinate? 1.1 squared. That's giving me 1.21. If I were to find the gradient of AE now, what would that be? Gradient of AE, that is 1.21 minus 1 divided by 1.1 minus 1. That will give me 2.1 now. Again, it's even better than before. It's closer to the actual gradient. If I were to keep doing this, let's take one more value. Let's take 1.01, for instance. What does that give us? 1.01 squared. That gives me 1.0201, and the gradient of AF, what does that turn out to be? 1.0201 minus 1 divided by 1.01 minus 1, that gives us 0.0201 divided by 0.01, and that's giving
One.
me 2.01. No, it's not 1, it's 2.01. Let
Okay,
me
sir.
try again. 0.0201 divided by 0.01, that's 2.01. Yeah. So now you can see the pattern. Where do you think the gradient is going? It's getting smaller and smaller, and then as it gets close to 2, it's not changing much now. So from 3, it went to 2.1, and then from 2.1, it went to 2.01. If you were to take another point after that, that would be like this 2.0001, like something like this. So this gradient seems to be reaching some value, and in this case, it's basically 2. So the gradient of the curve at this point A is actually going to be equal to 2. So that's the idea. We take one point on the curve away from the point at which we were looking to find the gradient. And then we say, what if we were to keep getting that point closer and closer to the point at which we want to find the gradient? The value of the gradient will keep getting closer and closer to the actual value of the gradient of the curve at that point. And you can see the pattern from that. And from that, you can argue that the gradient of curve at A, that should equal 2. Okay. So now without even drawing a tangent, you could think about this and get a very reasonable estimate of that gradient, which is going to be much better than drawing that tangent. Okay. Now that's the idea. That's the idea of differentiation. Now this is in this case, what we've done is we've just calculated the gradient at one particular point, and that point was point A. That's all that we've done. We've just found the gradient at the point A in this case. Now, what if we wanted to generalize this? Now, if we had to find the gradient at every single point like this, that will be pretty long, right? So if we had to find a gradient at this point, then again, if we had to calculate like 6 gradients like this to find the pattern, that will take quite long. So now what we can do is we can actually generalize this process. And how do we do that? Instead of saying that we want to find the gradient at the point A, which has coordinates 1 and 1, let's do it at a general point. And that will work like this. So again, let's consider that same function, which was y equals x squared. And now, instead of taking that point A as 1, 1, let's take a general point on the curve. Let's take this point. Let's call this point x, y. Right? Every point on the line is in this form, right? X, y. Every point has x coordinate x and y coordinate y. What if you wanted to find the gradient of the curve at this point like this, which represents every single point on the curve? Every point is x, y, right? Now we could use that same logic at this general point. So what we want to do is we want to find the gradient. Let me write down the statement here again. We want to find the gradient of the curve at any point on the curve that has coordinates x, y, right? Now, this is a general point on the line that we have taken. Let's apply that same process on this point. What we do is we take another point on this curve that is away from this original point. Let's take this point here, for instance. Let's call this point something. Let's call this point B. Let's call this original point A if we want, right? That's x, y. And we take that second point B in such a way that it is at a certain distance away from the first point on the x-axis. So this original point was A, this point B, let's say the distance of this point A from the point B on the x-axis is h units. Okay, it could be some other letter as well. It's just by convention that we use h here. We're saying these 2 points horizontally are h units away from each other. Okay. Now, if the coordinates of the first point were, if the x coordinate of the first point was x, what about the x coordinate of the second point? Can you think of that? If the x coordinate of the first point was x, what would be the x coordinate of the second point in this case?
X2.
X plus h. X,
Yes, it can be x plus h. Yes.
right? This is x. You can add h to that, and that gives you x plus h. Right? That's the x coordinate of the point B. So we can write it like this. We can say the x coordinate of B is x plus h. Now, what about the corresponding y coordinate? Now, think about this. We can also write it like this. For A, if the x coordinate was x, what is the y coordinate? If we were to write that in terms of x, y is equal to x squared. So we could think of this y coordinate of A like this as well. If the x coordinate is x, the y coordinate will be x squared. Now, similarly, if the x coordinate of B was x plus h, and this is the function that this point lies on, this is the equation that this point lies on, then the corresponding y coordinate should be x plus h whole squared. That should be the corresponding y coordinate that we have here. That's x plus h whole squared. So this second point that we have taken has these coordinates, x plus h and x plus h whole squared. So this y coordinate here will be x plus h whole squared. All clear until this point? Any problems, any confusion until this point?
No, sir.
Right? So we have taken 2 points like this. Point A is the point at which we want to find the gradient. And we're calling that xy, or in this case, x and x squared. And the other point is x plus h and x plus h whole squared. Now, let's find the gradient of this line. Let's find the gradient of this line AB. This is the line that we have. How do you find the gradient of the line AB? We use the gradient formula. We say gradient of AB, that is going to be equal to y2 minus y1 over x2 minus x1. What's y2? Y2 is x plus h whole squared. Let me write that down here. Let's say this is x1. Let's say this is, sorry, x2. Let's say this is y2. And let's say this is x1 and this is y1. So y2 minus y1, x plus h whole squared minus y1, which is x squared, divided by x2 minus x1, x2 is x plus h, minus x1, which is x. We get this gradient of AB. Let's simplify this and see what we get. We get x squared plus 2xh plus h squared using a plus b whole squared, that equals a squared plus 2ab plus b squared. We've just expanded this thing. Minus x squared, and in the denominator, we have x plus h minus x. What does that leave us with? Just h. Now, let's simplify this. X squared and x squared also get cancelled. What are we left with? 2xh plus h squared divided by h. We can take h common in the numerator. That leaves us with 2x plus h inside. In the denominator, we have h. H and h get cancelled, and we are left with 2x plus h. So what we have done is, we were looking for the gradient of the curve at this point, which has coordinates x and x squared. We took another point B at a distance, and we said, let's find the gradient of the line AB. What does that turn out to be? That's 2x plus h. Now, if we want an accurate estimate for the gradient of the curve at this point A, we want that second point to be as close to this first point as possible. So we want B to be as close to A as possible, right? As close as it can be. Now, as B comes closer to A, what happens to h? H will keep getting smaller. So in order to get a good estimate for that gradient, we want h to be as small as possible. Now, what's the smallest possible value of h that we can have here? We want it to be extremely small. That will be like 0.000 and then infinitely many zeros and then maybe one somewhere. So we can say h is actually going to just approach zero. We want h to be as minimum as possible. Why? Because we looked at this example before. As we got this point, the second point closer to the first point, the estimate of the gradient, it kept getting better. That's exactly what we're doing here as well. We want h to be as small as possible so that that second point comes very close to this first point. Now, what's the smallest possible value of h that we can have for that we can have in this case? We can say h should be extremely small such that it just reaches zero. When that happens, what does this gradient become? The gradient becomes 2 times x. And that actually gives us a general formula for the gradient of this function. That whenever we have a function like this, x squared, what is the gradient of that function going to be? The gradient of that function is going to be given by 2 times x. Now, if you wanted to find the gradient value at any particular point, you would just put the value of x of that point, and this expression is going to give you the gradient. So if you wanted to find the gradient at x equals 1, for instance, you would just put that here and you would say the gradient turns out to be 2 into 1, that is 2. If you want the gradient at x equals minus 3, you just put minus 3 inside this, and that gives you minus 6 as the gradient at that point. So this function that we had, x squared, 2x is the corresponding gradient function for x squared. So for any point xy on this curve, if we wanted to find the gradient is going to be given by 2x. All we have to do is put the value of x in that function, and that will give you the gradient at that point. Okay, so 2x is the gradient function of x squared. Does this process make sense? Where we are getting this? How we are getting this? From x squared, how we are getting the gradient function 2x? Right?
Yes, sir.
Now, for x squared, we are getting 2 times x. Okay, for x squared, we're getting 2 times x. Now, if we were to repeat this whole process for another function, which is x cubed, you would get 3x squared for that. So repeat this exactly same process on that. That will give you 3x squared. If you do that with x raised to power 4, that will give you 4x cubed. If you do that process with x power 5, that's going to give you 5x raised to power 4. And looking at these results, you basically get a general rule out of this. And that is, what you're doing is, if you had x raised to power n, as in anything as the power of n, you see the pattern here? Whatever number you have here, that's multiplying there, right? The number that you have in the power, that number is multiplying there. So we say it should be n times x, right? So that number is multiplying. And then what is happening to the power? The power was 2 earlier, it became 1 here. It was 3 here, it became 2. It was 4 here, it became 3. Looking at that pattern, what's happening to the power is that the power is reducing by 1, so that it becomes nx raised to a power n minus 1. So if you have a function x raised to power n, the gradient function for that is nx raised to power n minus 1. We get to a general rule using this process. Okay. Now this gradient function that we have here, this has another name. We call this derivative. We call this derivative of that function. It's called the derivative of this function. And this process that we are doing to find the gradient function from that original function, this process is known as differentiation. When we go from a function to its gradient function, this process is known as differentiation, and this gradient function has another name. We will be calling it the derivative of that function. And this is where this derivative comes from, okay, from this logic. Does that make sense to everyone? Any problem with this? This is a general rule now that we're getting. If you have x raised to the power n, the derivative of that is going to be nx raised to the power n minus 1. Make sense?
Yes, sir.
Okay, now let me get back here. What is differentiation about? In differentiation, we are basically looking to find gradients of functions. That's what we want to do. Now, for straight lines, we already know how to do that. We could do that like this. We want to find gradients of other types of functions as well. We could have any type of curve. So we want to understand how to find gradients of curves. And this is the process that we understood for this, that if we wanted to find the gradient at any particular point, we could follow a process like this, take another point on the curve, and then bring that point as close as possible to the point at which you're finding the gradient. Now, this process that we have done here, you have to know this. This is part of your syllabus. So sometimes they ask you to find all of these different gradients that we have calculated here, and then use that pattern to estimate this value. Okay. And then this part that we have done below, to generalize this is not something that you necessarily need to know. As in from which we got this general rule that the derivative of x squared is going to be 2x. Now, this was just for your understanding that how to connect that process to the actual differentiation process. This you are not going to be tested on. However, this will be something that you will be studying as the very first course in your university, Calculus 1. They will require you to understand this process. And now that you understand it, hopefully they will find that easier there, because when you do it at university, I actually found it very difficult to understand the first time because we had not done this in A levels. And what they do in university is they use some weird notations to just complicate this very straightforward concept. So now that you understand it, hopefully this will help you in your calculus course there as well. That's how this differentiation process works, but you will not be tested on this part in A levels. However, this thing where we had to find gradient at one particular point using these lines like this is something that you do need to know. You do get tested on this. So they will ask you to find these gradients and then use that pattern to estimate this value like this. So this is a process that you do need to know. And then this is a general rule that we are getting for differentiation. This rule is known as the power rule. And that's the next thing that we want to understand now. Power rule of differentiation. Power rule of differentiation. What does that power rule say? The pattern that we just figured out from those gradient functions. If you have a function like this, x raised to power n, the derivative of that is going to be nx raised to power n minus 1. Okay, that's going to be the derivative of this function. Okay, now this is the rule that you need to know about. Now, there's some notations that you need to be familiar with. First of all, there's one notation that will be in terms of functions. Now, we haven't done functions yet. However, function notation, at least you're already familiar with from O level. So for example, if you have y equals 2x plus 3, if you have a function like this, you could write it like this: f of x equals 2x plus 3, right? At least in this notation you are familiar with, right? So sometimes they write functions in this function notation. So if you have f of x equal to x raised to power n, if you have something like this is your original function. The derivative of that function in this notation, that is going to be denoted by f prime of x. So we have this dash on top. This represents the derivative of f. Okay. So let me write that here. This is function f, and this is the derivative of f. So function f is f of x, and derivative of f is f dash of x or f prime of x. All right. So that's a notation that you need to be aware of. That's one notation. There's another notation as well. We will also write it like this. If the original function is y equals x raised to power n, that gives us the derivative like this, dy over dx. That's another notation that you use for differentiation. It's nx raised to power n minus 1. dy over dx equals nx raised to power n minus 1. Now, how do you read this thing? This basically means derivative of y with respect to x. Okay, derivative of y with respect to x. Y is the function of which you're finding the derivative. X is the variable in which that function is defined. So we read it like this: derivative of y with respect to x. This notation actually comes from that. Remember, what does the derivative represent? The derivative represents gradient function. What's the gradient? How is the gradient defined? Let's get rid of this side. How is the gradient defined? Gradient is defined as change in y over change in x. So we often write it as delta y over delta x. Now another notation that we use for delta looks like this: delta y over delta x, change in y over change in x. That is where this comes from, dy over dx. So instead of delta, we often write it like as d. That's change in y over change in x. And that's what the gradient represents as well, dy over dx. Okay. So dy over dx just means derivative of y with respect to x. That's given by nx raised to power n minus 1. Okay. So that's a general rule that we have now. Okay. Now, let's take an example. Let's take a couple of examples, and then we'll do more examples in the next class. We will not be spending too much time on this right now. Let me just give you a few examples, and then we end for today. So let's say we have a function like this: y equals x raised to power, I don't know, let's say 9. What would be the derivative of that? dy over dx. What would be that? You use that rule that you had there. X raised to power n, this becomes nx raised to power n minus 1. So what you're doing is you're multiplying by the power. So power gets multiplied. You have 9 here. And then you subtract 1 from the power. So the power 9 is going to become 9 minus 1, and that gives you 9x raised to power 8. And that's the derivative of x raised to power 9. Okay, so we can also actually write this rule like this. We can say for differentiation, for using the power rule, we're doing two things basically. Number one, you have to multiply by the power. This is going to be used a lot throughout this topic. And you'll find this in paper 3 later as well. So you need to remember the process of doing differentiation for functions like these. You multiply by the power. Number two, you say you subtract 1 from the power. These are the two steps that you have to follow here in order to apply this power rule. you multiply by the power and subtract 1 from the power. Okay, that's exactly what we're doing here. We're saying let's multiply by the power, that's 9, and then subtract 1 from the power. That's 9x raised to the power 8. That gives you the derivative. Now, what if it was something more complicated than this? What if we had, let's say, y equals 7x raised to the power minus 2. Now remember, if you have a constant outside that's multiplying, that remains as it is. That does not change. So 7 is going to remain as it is. So any constant multiplying outside this is not going to change. So 7 remains as it is. Okay. And then on this part, you apply the power rule. How does the power rule work? Multiply by the power. So you multiply by minus 2. Subtract 1 from the power. So it becomes x raised to the power minus 2 minus 1. What does that give you? Minus 3. And now you can simplify this. This gives you minus 14 x raised to the power minus 3. If you want, you can write it as minus 14 over x cube as well. And that will be your derivative. Okay. Let's take another example. Let's say you had something like this. Y equals minus 4 over 3 into x raised to the power 5 over 2. What about this? How would you differentiate this? Anyone? So take 30 seconds and let me know what the derivative of this function should be.
Sir,
Yes.
sir, it would be minus 4 over 3 times 5 over 2 raised to power x to the power 3 over 2.
Multiplied by x raised to power 3 over 2. Yeah, so that's good. Minus 4 over 3 remains as it is, right? That's a constant multiplying. We will not change that. 5 over 2 gets multiplied with that. So we multiply by the power. And then we subtract 1 from the power. So it becomes 5 over 2 minus 1. So what do we get from that? Minus, so let's simplify this. 4 and 2, they get cancelled. You have 2 here, minus 10 over 3 into x raised to power 3 over 2. That's the derivative. Okay. What if we had something like this? If we had y equals, let me actually just complete this today. It's just going to take like 5-7 more minutes. So we can do the next thing tomorrow then after that. Let's say we have 5 over 7 square root of x. What about this? Take 30 seconds, write down your answers in the chat box. Okay, don't speak yet. Write down your answers in the chat box quickly. What's the derivative of this function? dy over dx. Yes, does anyone have the result? Can I have your answers in the chat box? Hazim, that's not correct. Think again. You're missing something. Abdullah, the constant outside does not seem to be correct. Can the rest of you try as well? Let me know in the chat box what your answers are. Okay, let's try this. So first of all, we need to write this in power form. We can't differentiate it directly like this. We need to write it in this form first of all. X raised to the power something in the numerator. Now this is in the denominator right now. X is in the denominator. So what we have to do is we have to write this in the numerator first of all. So we will write this function like this first. We'll say this is y equals 5 over 7. 5 over 7 remains as it is. X, square root of x, that is x raised to power 1 over 2. If we want to take it to the numerator, in the numerator, it's going to become x raised to power minus 1 over 2. Right? Remember, there's no power on 7. We are not going to take 7 above. We're just taking x in the numerator. When it goes to the numerator, the power becomes negative. We have minus 1 over 2 here. That's the function. Now we can differentiate it. The constant remains as it is. 5 over 7 remains as it is. We multiply by the power, which is minus 1 over 2, and we subtract 1 from the power. Minus 1 over 2 minus 1. What does that give us? Minus 3 over 2. We simplify this now, and that's minus 5 over 14 into x raised to power minus 3 over 2. That's the derivative that we get from this. All right. Any problem with this? Any problem with this? No? Okay. Now, let me just write down a few more examples. Let's say you have y equals 7x. How do you differentiate this now? dy over dx, derivative of 7x. Let's apply the power rule on this. 7x means it's 7x raised to power 1. If we apply the power rule, what does that give us? 7 into 1 into x raised to power 1 minus 1, right? And what's that going to give you? That's going to give you 7 into x raised to power 0. X raised to power 0 is 1, and that just leaves us with 7. That is actually a general rule that we can remember, that whenever we have y equal to some constant into x, the derivative of that is always going to be this constant that is multiplying outside. This constant outside is going to be the derivative, k. Okay, that's what's happening here. The derivative of 7x is just 7. Why? Because every single time what's going to happen is 1 is going to get multiplied. That does not change anything. Then the power of x is going to become 0, and that becomes 1 as well. So we're just going to be left with this constant. And we could think of it using that straight line form as well. Y equals 7x is actually a straight line. Y equals mx plus c. Compare with that. What's the gradient? The gradient is 7. So the derivative from this function is going to turn out to be 7. Okay. So whenever you are differentiating something with x power 1, you can write it like this directly. If you had, for instance, y equals minus 7, or let's say minus 8 over 3 times x, the derivative of that you can write directly as minus 8 over 3. Okay, so that's a general rule that you can remember. You just have x power 1, the constant, the coefficient with that, that's going to be the derivative. Okay. And then if you had something like this, for instance, y equals 4, what's the derivative of that? How do you apply power rule to this? Y equals 4. How do you apply power rule to this?
Sir, it would remain as it is.
It will remain as it is. So dy by dx is going to be 4.
Yes,
Dy
sir.
by dx is,
Sir, or
so
it can be 0. Power would be 0 if we take 1 down.
okay, so we can write this as, we can write y equals 4 as y equals 4x raised to power 0. Right? If we want to write it in power form, it becomes 4x raised to power 0. And now if you were to apply the differentiation rule to this, what is this going to become? 4 into 0 multiplied by the power, subtract 1 from the power. It doesn't make any difference because we have 0 multiplying. So we have x power 0 minus 1. Everything becomes 0. The derivative turns out to be 0. And that's a general thing that you can remember as well. Y equals 4. What kind of a line is this? It's a horizontal line, right? Y equals 4 is a horizontal line. Horizontal lines have 0 gradient. And using power rule as well, you're getting the derivative equal to 0. So that's a general thing that you can remember now as well. Whenever you have y equals k, y equals some constant, the derivative of that is going to be equal to 0. Now, these are not some separate rules as such. These are just some special cases of this power rule itself, right? We're using power rule there as well. However, when you have something like this, there's no need to apply that rule explicitly as such. You can just write down the derivatives directly. That's why I'm writing them separately. So you can remember this. Whenever you have something into x, the derivative is just going to be the constant with that x. And when you have just a constant, the derivative is going to be 0. One last example and then we end. If you have something like this, y equals minus 2 over 3 into x raised to power 5 over 7 plus 5 over 2 under root x minus 3x plus 7. If you wanted to find the derivative of this thing, now you have multiple terms, right? You have multiple terms. You have this terms, you have this term, plus something, then minus something, then plus 7. Earlier, we just had one term in all of these examples. When you have a function that has multiple terms like this, you can find the derivative by just finding the derivative of each of these terms separately one by one. So find the derivative of this thing separately, this separately, this separately, and this separately. Find the derivative of every single term separately, okay? Let's look at the derivative of this first. In fact, before we do that, let's convert this to standard form. Let's convert all terms to standard form first of all. So the second term in particular, that's not in standard form. So we can write that in power form first. 5 over 2 remains as it is. Bring x to the numerator. Its power is going to be minus 1 over 2, right? In the denominator, it was plus 1 over 2. When it comes to the numerator, it becomes minus 1 over 2. Then we have minus 3x and plus 7. Okay. Now we find the derivative. Let's find the derivative of the first thing, minus 2 over 3 as it is. Multiply by the power, it becomes 5 over 7. Subtract 1 from the power. 5 over 7 minus 1, that's going to be minus 2 over 7. Plus 5 over 2 as it is, multiplied by the power, that's minus 1 over 2, into x power minus 1 over 2 minus 1, which is minus 3 over 2. Then what's the derivative of minus 3x? We just learned this. If we have minus 3x, the derivative of that is just going to be minus 3. And then what about the derivative of plus 7? That is just going to be 0. Okay, so you can just ignore that as well. It's not necessary to write that 0. Now you can simplify this, and that gives you minus 10 over 21 x raised to power minus 2 over 7 minus 5 over 4 x raised to power minus 3 over 2 minus 3. That's the derivative that we were looking for. So if you have multiple terms like this, you just find the derivative of each term separately like this. Is that okay? Any questions, any problems? Let me know. We're just going to end with this if there are no problems.
Sir,
Yes, Abdullah.
sir, won't we add plus c at the end?
No, that's for integration. We don't have to do that in differentiation.
Okay, sir.
That happens in integration. Okay. All right. So that's it for today. I'll see you again in the next class, in which we will extend this power rule to other types of functions. So for example, we will learn how to differentiate, for instance, something like this, 2x plus 1 whole raised to power 2 over 3. If you had something like this, what would you do with that? That's for the next class. And along with that, we will learn some applications of differentiation, that where is this differentiation going to be used. Okay. But that's it for today. I'll see you again in the next class. Allah Hafiz.
Allah Hafiz, sir.
Enough, guys.